Hi dear students, in our last video we studied the concepts of gravitational potential energy and we derived the conservation of mechanical energy in case of freely falling body under gravity. And today also we have to continue our discussions related to the mechanical energy. So if you think of the other type of the gravitational, other than the gravitational potential energy, one more kind of potential energy we have, that is the elastic potential energy, which is somehow associated with the restoring force. So for better understanding of this elastic potential energy, let us have the example of a spring. If we have the spring, let us stretch the spring. In order to stretch the spring, we are applying some external force, and if we remove the external force, the spring will regain its initial position, that is a restoring force. That means the spring possesses a restoring force. The spring possesses a restoring force. And if we are going to stretch the spring by applying more force, that means if the displacement is more, the restoring force is also more. And now ಜಾಸ್ತಿ stretch ಮಾಡಿದ್ರೆ, if displacement is more, the restoring force is also more. If stretching is less, the restoring force is also less. ಹಾಗಾದ್ರೆ the restoring force of a spring depends on the stretching, that means or the compression, which is nothing but the displacement from its mean position. So let us just consider the relations. We can consider Fs is the spring force or a restoring force. This spring force is directly proportional to displacement. Let us have the spring. So if this is at rest position, let us apply some force and we are going to displace that spring through a distance of x. That means if displacement is less, the restoring force is less. If we are going to displace that to greater distance, that means the restoring force required is also more. So we can write spring force is directly proportional to displacement. And it is very important to know about the directions. See, in this we are applying the force, that is external force, in downward direction, so the displacement is also downwards, but the restoring force is acting vertically upwards, isn't it? Therefore we can write Fs is proportional to minus x. They have same magnitude but they are acting in opposite directions, and this can be equated by using the constant, that is k, and we are calling that as the spring constant or force constant, where k is the spring constant. So Fs is equals to minus k into x. We can call this one as a Hooke's law. It is called Hooke's law, where the spring force is directly proportional to displacement. Since they are acting in opposite direction, we are writing that with negative sign. Therefore Fs is equals to minus k into x. And now we have to give the expression, or we have to arrive the expression for spring force, and we have to give the expression for potential energy associated with this spring force. Let us focus on the potential energy of the spring force, that is called elastic potential energy. So we are thinking of elastic potential energy. Elastic potential energy. So let us consider a spring which is horizontally mounted on the smooth surface. If there is no displacement, if x is equals to 0, we can say the spring force is also 0. Just we have a spring and we are mounting that on a smooth surface horizontally, not vertically. We are mounting that horizontally. If there is no displacement of the load, it is at rest, so the spring is at its mean position, so the spring force is also 0, or the restoring force is also 0. I am considering the second case where the spring is displaced through a distance x. Compared to this, here we are stretching the spring and we are displacing that through a distance x. So the restoring force will be in opposite direction. So this is the direction of Fs. The displacement is in forward direction and the restoring force is acting in backward direction. This is the case of stretching of the spring. The third case, see, compare the first and third diagram. We are compressing the spring. That means again we are making some displacement from its mean position. So the displacement is in backward direction. So the spring force is in forward direction. So by this we can consider the spring force and the displacement, they are in opposite directions. And we know that if displacement is more, spring force is more. So now we have to consider whatever the mechanical work we are applying in order to stretch the spring or in order to compress the spring, that work done will be stored as the potential energy and we are calling it as elastic potential energy. So we can have the graph between the spring force and the displacement, and with the help of the graph also we have to get the expression, and by using the expression of the work also we have to get the expression, and we have to show that both the expressions are same. So let us first focus on the expression by considering the definition of the work. So what is that of the spring? We got the relation, that is Fs is equals to minus k into x. Fs is equals to minus k into x. Let us find the amount of work done for stretching or for compression of the spring. That amount of work done will be stored as a elastic potential energy. So we know that the amount of work done is equals to force into displacement. Let us consider we are displacing the block through a small displacement dx. So the total work done will be the integration of all such small work done. Repeatedly we are using the concepts of integration. So here we are taking the block from mean position to extreme position. So we have to consider it has been displaced through small displacements dx. Therefore the total work done W is equals to, in general we are considering work done as force into displacement. Here the force is the spring force and the displacement is the small displacement. To get the total work done, we have to reach from initial position to extreme position, that is xm. Initial displacement is 0 and maximum displacement, that is xm, to reach the extreme position. So W is equals to force into displacement, and the displacement varies from 0 to xm. So the total work done can be obtained as W is equals to integration of Fs into dx from x is equals to 0 to maximum displacement. So now W is equal to, so since spring force is a constant and here the variable is dx, we can vary the dx, or the spring force got the expression. The spring force is given by Fs is equals to minus k into x. Please substitute that spring force expression here, where the displacement is from 0 to maximum position and Fs is replaced by minus k into x into dx. So now W is equals to, since k is constant, let us take it out. I am going to keep that minus sign as it is, minus k integration 0 to xm x into dx. And here we must recall the general formula of integration, that is integration of x power n is x power n plus 1 divided by n plus 1. So here we have, in the place of power is 1. So x to the power of n is that integration formula integration of x power n into dx is nothing but x power n plus 1 divided by n plus 1. So in the end of the is 1 error. So what is integration of x into dx? It is x to the power of 1 plus 1 by 1 plus 1. It is x square by 2. Therefore I am writing W is equals to minus k into integration of x into dx is nothing but x square by 2 and the limit from 0 to x. After integration, we have to apply the limits. So if you apply the limits, we get W is equals to minus K by 2, because 2 is constant. Just the variable is x, right? So the upper limit is xm square minus the lower limit is 0. So finally we got that expression for work done is minus half into K xm square, minus half into K xm square. So this is by using the expression of work done. So let us get the same amount of work done, that is for spring force, by graphical. So in order to have the graph, we must have the two variables, that is the spring force and displacement. And the very important that we came to know that spring force is directly proportional to displacement, but they are acting in opposite direction. So I am going to consider the coordinate system. Along the x-axis, let us take the displacement, and along y-axis, let us take the force, that is spring force. So this is positive x, and this is negative x, this is positive y, and this is negative y. So initially, let us consider if displacement is in forward direction, the restoring force is in backward direction, but they are directly proportional to each other. That means if displacement increases, the restoring force also increases, but they are in opposite directions. If the displacement positive ಆದರೆ spring force ಏನಾಗ್ತಾ ಇದೆ ನೆಗೆಟಿವ್ ಆಗ್ತಾ ಇದೆ. So x value positive ಇರಬೇಕು, force value negative ಇರಬೇಕು. ಯಾವ quadrant ಬರುತ್ತೆ? That is fourth quadrant, where x value is positive, force value is negative. So as x increases, the f also increases. So we are going to have the linear curve like this. This curve is linearly increasing in the same way. In case of compression, if x is considered to be in backward direction, then restoring force is in forward direction. That means again they are in opposite directions. Here x is considered to be negative, then f is, that is the spring force, becomes positive. So displacement is negative, that means displacement is along this axis. The spring force is positive, that means upward. So we are going to have this one. So this graph represents the variation of the spring force with respect to the displacement. So now we have to get the expression for work done, right? So let us call this as the origin. So just I am going to give a name. This is B, and the normal for that is B M. So the area under the force displacement curve gives the work done. So to find the work graphically, we have plotted the graph of the displacement as well as the spring force. So to find the work done, the area under the curve gives the work done. So in case of stretching, displacement is positive and that the spring force is negative. So we got the area under the curve. We have to find this area of OBN. So for a triangle, work done is equals to area under curve. Area under curve. So W is equals to, so here we have the triangle OBN. So half into base into height. There is a formula for area of triangle. So area under the curve is nothing but triangle. So half into base into height. So here half. What is base? Base is nothing but ON. ON gives the displacement, and here the maximum displacement, that is xm. So I am writing this base as xm into height. Height is nothing but bm. So it is the y component, that is nothing but the spring force. So I am writing it as minus f. Yes, or simply we can write fs. Later we can consider that fs value. So fs is nothing but minus k into x. So let us substitute that value, that is half xm. Instead of fs, what we have to write? Minus k into displacement is maximum, that is xm. Because we have fs is equal to minus k into m. Here the displacement is maximum. So this fs is replaced by minus k into m. So we got w is equals to minus half k xm square. So here also we got w is equals to minus half k xm square. That is by considering the formula of the work done. And graphically also we got the same expression, w is equals to half k xm square. So this is the amount of work done by the spring force. So now this amount of work done by the spring force will be stored as potential energy, and already we know that the negative of work done is called potential energy. The negative of work done is called potential energy. So we got the expression for work done. In order to get the expression for elastic potential energy, we have to consider the negative of work done, because we have the relation. In your previous video we discussed that V is equals to minus F into X, isn't it? So negative of work done is considered to be the potential energy. Hence the expression for elastic potential energy. I am going to write the final expression here. Let V be the elastic potential energy, and we got the negative of work done is called potential energy. Therefore V is equals to minus W, that V is equals to minus of minus half k xm square. It becomes half k xm square. So this is the expression for elastic potential energy. What is the expression we got for elastic potential energy? V is equals to half k xm square, where k is the force constant and xm is the maximum displacement in case of the stretched spring. So here also we have to consider the conservation of mechanical energy. So we have to prove at each and every point of the displacement to extreme position or at the mean position or because of compression, the mechanical energy of the oscillating spring is again conserved. So in order to prove that, let us just so please you have to take a screenshot, and or you can have a reference of the notes, nothing to worry about it. So now we have to prove the conservation of mechanical energy, isn't it? So here also we have two kinds of energies, the potential energy and the kinetic energy, and there is interconversion of potential energy to kinetic energy and kinetic energy to potential energy. When the spring is in rest position or if displacement is zero, the displacement is zero, this is considered to be mean position, and we are going to stretch the spring, and this is extreme position. So let us have the spring like this. So we have attached some load. So it is at rest, it is called mean position. So if we displace that, it is going to execute oscillation. That means this is the extreme position. So it will reach the mean position, and later it will get the extreme position on other side. See, this is a resting position, right? So I am going to apply some force. It is executing oscillations. That means mean position, we are taking that to extreme position. If we leave that, the spring force brings that back to mean position and it undergo compression. That means the load attached to that spring will continuously execute oscillations between two extreme positions. One is because of the compression, the other one is because of the expansion. So spring is oscillate ಆಗ start ಮಾಡಿದ್ರೆ mean position ಇಲ್ಲಿದೆ, extreme position on other side, and it comes back to mean position and it reaches the extreme position on the other side. It is executing oscillations. So let us consider three different positions. This is the mean position, this is the extreme position, and this is the extreme position. See, initially we have to begin from extreme position. So as we reach or we take the load to the extreme position, it will be at rest. Isn't it? So because of its extreme position, there will be stored form of energy, and that stored form of energy is called potential energy. That means at extreme position, the potential energy is maximum. At extreme position, the potential energy will be maximum. And if we allow that the load, it starts to move towards the mean position. That means because of spring force, it is making its displacement towards the mean position, so that potential energy gets converted to kinetic energy. So as we allow the load to execute oscillations From extreme, it reaches the mean position. So at mean position, the displacement becomes 0. So potential energy will get converted to kinetic energy and speed becomes maximum. Speed becomes maximum. So kinetic energy depends on speed. As the speed becomes maximum, we can say at mean position the kinetic energy is maximum. Kinetic energy is maximum. But at mean position the potential energy becomes minimum. So you can consider V or U becomes minimum. Potential energy becomes minimum. And as we observe, the load will, yes, we can have the pendulum also. So ಇಲ್ಲಿಂದ ಬರ್ತಾ ಇದ್ರೆ mean position ಕಡೆಗೆ ಬಂತು ಮತ್ತೆ it will reach us the extreme position, isn't it? So ಇಲ್ಲಿ potential energy maximum ಇದೆ. Mean position ಗೆ ಬಂದ ತಕ್ಷಣ it will be gets converted to kinetic energy. So kinetic energy becomes maximum. Again it will reach us the extreme position on another side. So extreme position ಗೆ ಹೋದ್ರೆ it acquires some position because of its position or because of compression. It is possessing again potential energy, that is potential energy becomes maximum. So ಈಗ extreme position ಗೆ ಹೋದ ತಕ್ಷಣ velocity ಏನಾಗುತ್ತೆ 0. That means kinetic energy is 0. At which position? Extreme position. Kinetic energy is 0 at extreme position. That means at extreme position the complete kinetic energy will be gets converted to potential energy. Like this, the kinetic energy and potential energy, they are interconvertible, but the total sum of the energies, that is the mechanical energy, is constant. Even we are taking the example of the oscillating spring. Okay, so extreme position rate, because of its position it is possessing potential energy. Mean position, displacement 0. So it starts to move from extreme towards mean. So velocity becomes maximum, and because of that it is going to be gets compressed. That means it is reaching the extreme position on another side. So ಹಾಗಾದ್ರೆ extreme position ಹತ್ರ potential energy ಜಾಸ್ತಿ ಇರುತ್ತೆ, mean position ಹತ್ರ kinetic energy ಜಾಸ್ತಿ ಇರುತ್ತೆ. Extreme position ಹತ್ರ kinetic energy 0 ಆಗುತ್ತೆ, mean position ಹತ್ರ potential energy will be equals to 0. So just I am going to represent that with the lines. So maximum potential energy, that we can take U or V, it is maximum. So as we reach towards mean position, this potential energy becomes decreasing and becomes 0. Again if we move on another side, then potential energy increases and becomes maximum. And the kinetic energy at extreme position it is 0. As we are moving towards the mean position, velocity increases. As velocity increases, kinetic energy also increases. That means as potential energy decreases, the kinetic energy starts to increase and becomes maximum at which position? At mean position. As we move away from mean position to another extreme position, the velocity decreases and finally comes to rest. So as potential energy increases from mean position to extreme position, the kinetic energy goes on decreasing and finally becomes 0 at extreme position. But if we get the total sum of kinetic energy and potential energy at any part of the movement, it is constant. Hence we are considering the mechanical energy in case of the oscillating spring also remains conserved. It is also remains conserved. So we have to get the expression for elastic potential energy, that is W is equals to minus half k xm square with the help of formula of the work and with the help of the graph, and finally we have to get that negative of Laplace potential. So V is equals to half k xm square, or we can take U is equals to half k xm square, that is elastic potential energy, and we are proving the conservation of mechanical energy even in case of the oscillations of the spring. So this is in mean position, and this is stretching because of that extreme position, and this is compression because of extreme position. So spring rest ಆಗಿದೆ, ನಾವು ಸ್ಟ್ರೆಚ್ ಮಾಡ್ತೀವಿ extreme position ಹೋಗುತ್ತೆ, ಅಲ್ಲಿಂದ ವಾಪಸ್ ಮೀನ್ ಪೊಸಿಷನ್ ಬಂದು ಮತ್ತೆ ಕಾಂಪ್ರೆಸ್ ಆಗಿ ಇಟ್ ಇಸ್ ಎಕ್ಸಿಕ್ಯೂಟಿಂಗ್ ಆಸಿಲೇಷನ್ಸ್ ಫ್ರಮ್ ಮೀನ್ ಟು ಎಕ್ಸ್ಟ್ರೀಮ್ and extreme to mean, mean to extreme, and coming back from extreme to mean, and at extreme positions, because of its position, it possesses potential energy, and at mean position, there is maximum velocity, so kinetic energy becomes maximum. At extreme positions, kinetic energy is 0, and at mean position, kinetic energy is maximum, potential energy is 0. So, interconversion of kinetic and potential energies takes place, but the sum remains conserved. So, we have various forms of energies, and we well know that the law of conservation of energy. Energy can neither be created nor be destroyed, just it can be converted from one form to another. Isn't it? So, we have wide varieties of energies. Let us have the few here, that is heat energy, chemical energy, electric energy, nuclear energy, like this light energy, sound energy. We have many kinds of energies. So, heat energy, it can be obtained because of friction. Isn't it? If you are going to rubber pumps, the mechanical energy will get converted to heat energy, so it is obtained or derived from some form of energy. So heat energy can be obtained because of the kinetic friction. Chemical energy is energy stored because of the chemical bonding. Isn't it? It may be sigma bond, pi bond, whatever it may be. Because of the chemical bonding, there will be some stored form of energy that we have to call it as chemical energy. Electrical energy, electrical energy is energy because of the motion of the electric charges, isn't it? If the charges are said to be in the state of motion, then they are going to constitute electric current. Then we have nuclear energy. It is the energy stored in the form of the potential because of the holding of nucleons together with the nuclear force. So it is also going to be related with the Einstein's mass energy relation, that is E is equals to delta m into c square. That means here the nuclear energy is obtained from the destruction of the nuclear mass. The mass will be get converted to energy. So if we have the radioactive sample, if it is highly radioactive means if it is highly reactive, so it will undergo disintegration. Disintegration means its mass will be reduced, and that mass will be obtained in the form of energy by Einstein's mass energy relation. E is equals to delta m into c square, where c is the velocity of light in the vacuum. Isn't it? So like this, we have various forms of energies, and we must finally conclude that with the law of conservation of energy. Energy can neither be created nor be destroyed. It can be just converted from one form to